Okay, so in the last lecture we start with the problem of a cone floating and we had to find the condition for it to remain in the upright position. So we use two formulas. We use the formula for the Archimedes principle, and also then we use the formula that GM should be greater than 0, the metacentric height should be greater than 0, and use that as the condition for the cone to float upright. Now let us look at another problem which will talk which is again similar. It is another cone, but it is floating in the opposite direction like this. So the cone is floating like this. The cone is floating in the upper in this condition. Half part of the cone is outside. Let us call that distance as d. This is one and this is other. This is obviously what we call as the draft T, and this distance is put as FB. Usually we call the distance outside freeboard. So that region outside the cone, region outside the water is always called as a freeboard, and and this is the draft, that is T. The whole thing is H, the height of the cone. So therefore you get H is equal to T plus FB. So the part of the cone inside plus outside is the total height of the cone. Now first of all, so the question is, what is the condition under which this system will float in this upright condition? What we have to do is solve for one, the Archimedes principle, and 2, we need to solve for GM greater than 0. We usually put GM equal to 0 and then GM greater than 0 gives you the condition for stability. So Archimedes principle given here would be, the first thing, the Archimedes principle given here would be that gamma c, the weight of the cone, into pi, this distance is d, this distance is small d, pi d square by 4 into h. This will give you the total mass of the cone. This is the volume of the cone. Pi d square by 4 is the surface area of the cone here, and into h multiplied by h gives you the volume of the cone, into gamma c, that is the density of the cone material. It gives you is equal to the weight of the water displaced, is equal to pi by 3 into 4 d square h minus d square FB. This comes by, so this is equal to this volume. Okay. So this gives you this total volume, the volume of the cone, and oh sorry, there is a 3 also here I missed. 1 by 3 pi r square h is the volume of a cone. So 1 by 3 pi d square by 4 h is the volume of the cone. So this is the total volume of the cone, and this is this volume. So you get same thing, pi by 3 into 4 into d square h. This gives you this total volume minus this volume. This volume is equal to d square into FB. In d square is this d square into FB. I think it is obvious how this equation has come about. So this is the Archimedes principle. The mass of the cone is equal to the weight of the liquid displaced. If it is not clear, again I will repeat this, that is, this is the total volume under the water. Okay, this is the total volume under the water line. This is, let us call this as the water line. So the total volume under the water line is equal to pi is equal to this total volume, pi by 3 into 1 by 3 into pi d square by 4 h is the total volume minus the volume of the top portion will give you this volume underwater, which is what we call as displacement. So, pi by 3 into 4 d square f b, d square into f b, f b is this height, freeboard, that is what we call as a freeboard. This is a term not only used in for this problem, but freeboard is a common term used in naval architecture. It refers to the region of the ship that is outside the water. So, the region that is visible outside water, that region we call it as the FB, the freeboard. So, this is the Archimedes principle. This is the first equation that we have. So, from this we get FB is equal to, just by doing some arithmetic on the previous equation, by gamma w into d square h by d square. Now, if you apply similarity theorem to, so this is how we have here, this is the water line. So, we have here FB, we have here total distance h, d, d, this distance and this distance. So, if you put similarity theorem, if you use the similarity of these two triangles, that is this small triangle and this large triangle, then you get d by d is equal to FB by h. This gives you a similarity formula, and combining this equation with this gives you FB is equal to gamma w minus gamma c by gamma w the whole power 1 by 3 into h. If you just do this, you will get this expression, and let us put beta equal to this thing, this whole expression as. So, this gives you FB is equal to beta h, where beta is given by this parameter that we have given here, gamma w minus gamma w is the density of water minus gamma c, the density of the cone, divided by gamma w whole power 1 by 3 h. So, FB is equal to beta h. Okay. Then draft T is equal to h minus FB is equal to 1 minus beta into h, that is the draft of the cone. Then you will have KB of the cone. KB of the cone is given by this gives you the diameter, this gives you the center of buoyancy. So, what you really have here is the centroid of this. So, what we want is the centroid of this region. Okay. So, this region. So, the centroid of that is given by this formula d plus 2d by d plus d. Now, this is the formula for the centroid of a trapezium. So, the centroid of the trapezium is given by this formula. There is no other way other than to just remember it as such, because centroid of a trapezium we hardly use anywhere, but this is how this is how the trapezium's centroid looks like. So, you just have to by heart this expression for the centroid of a trapezium. We might be using it again and again. So, just memorize this. So, this gives you T by 3 into d plus d. This gives you the KB, the centroid of the trapezoid. Then BM is equal to I by del. This we know. I, what is it? It is the centroid of the water plane area about a transverse axis. Now, the centroid of a in this case, the water plane area is a circle, because we are talking about a cone. The water plane area, the centroid of the water plane area, the moment of inertia of the water plane area about any axis is given by pi d power 4 by 64. We use the small d and not the capital D because we are talking about the water plane. Water plane is the water plane area is the area at the region where the water line exists. Okay, at the point of the water line, the area that you have is what you call as a water plane area. The water plane area's diameter is small d. So we have pi d power 4 by 64 as I is equal to pi d power 4 by 64. Now d is equal to okay, then so d is equal to beta d that comes from above, and therefore this is equal to pi beta power 4 d power 4 by 64. And del is the underwater volume. We are talking about the volume of a part of a cone. You can take that as the total volume minus the volume of the cone at the top will give you the volume underneath. That is equal to pi into 1 minus beta cubed into d square h divided by 3 into 4. It is 1 by 3 pi r square h always. That is what we have done here, 1 by 3 pi r square h. Then we get Bm therefore equal to 3 by 16 beta power 4 by 1 minus beta cubed into d square by h. So it comes like this. For the Bm, the metacentric radius, Bm becomes this. Now the center of gravity of the cone, as we know, is the center of gravity of the triangle, this whole triangle, and the center of gravity of a triangle is 1 by 3 from the base, 1 by 3 h, 1 by 3 of the height from the base, or 2 by 3 of the height from the top. So therefore kg is equal to 1 by 3 of h, 1 by 3 of h or h by 3. So this is the center of gravity. Now the resulting metacentric height, therefore the resulting metacentric height Gm is therefore given by Kb plus Bm minus Kg. This is the metacentric height, is equal to 1 minus beta into 1 plus 2 beta divided by 1 plus beta plus 9 by 16 beta power 4 by 1 minus beta cubed into d by h the whole square greater than 1. So this is the condition for Gm. This is the cone is so if this happens, this is by putting the condition that Gm greater than 0. If you put this condition, you get this expression, and this is the condition for the cone to be stable. And so this is the condition for the cone to be stable. So you get an expression like this. So this is a problem. So whenever you are asked a problem on how when you are asked a problem on how to calculate how to figure out if something is stable or not, what we need to do is first apply the Archimedes principle and then apply the condition that Gm greater than 0. So by combining these two formulas, you will be able to get the condition for the object to remain in a stable condition. Now let us consider another problem, that is, there is a parallelepipedic barge, which means this is a rectangle, and it's all such barges are also called as box shaped barges. It is like this. So your cross section is a rectangle, and anywhere it's across, the whole thing is a parallelepipedic barge, means a whole thing is a box, it's just a rectangular box. So initially this is the water line WL, and W0 L0 is the initial water line. and when it tilts, it becomes like this, W phi L phi. So here there is a region immersed somewhere here, the center of buoyancy of that region Bi, B immersed, and here is a region emerged, it is known as Be, the emerged region. So this is an emerged region and this is an immersed region. So two regions. Now from our knowledge we should know that this region is 2 by 3 B by 2. This whole thing is B. This whole thing is B, which will imply that this region is B by 2. So 2 by 3 of B by 2 will give you this distance, which is equal to B by 3. So this distance is B by 3 and this height is this is whole thing is H and this region is T. This region is T and this region is H, and B immersed, this height will be 2 by 3 of this whole distance, this distance. So this distance we do not know, but we know that it is healed through an angle phi. So this distance is equal to B by 3 tan phi. That much we know. This distance is equal to B by 3 tan phi. If this is B by 3, if this is B by 3, if you put a triangle here, this whole distance will be B by 3 tan phi, and this, so this is how you calculate the center of gravity. Okay. Now suppose you are asked to find the transverse center of gravity and the vertical center of gravity, transverse center of buoyancy and the vertical center of buoyancy, which are known as transverse center of buoyancy and the vertical center of buoyancy. So you are asked to find them. In short notation we write it as TCB and VCB. So with this figure here we will do it. So let us make this table. This is the solid we are talking about. Then you will have the volume, then you will have TCB, and you will have the moment. So initially we are talking about the initial condition, that is without any tilting. Initial condition, the volume is LBT, the volume underneath the water line, which we call it as the displacement, is LBT because it is a rectangle. It is just length into breadth into its depth, which is T, the draft. So LBT, and the TCB, it is the everything is 0 here. This is considered to be the origin, so this is 0. Then there is a submerged wedge. For the submerged wedge, its volume is equal to half base into altitude. Volume will be half base into altitude, H will give you the area into length. So this will give you the volume of the submerged portion. So this will be half base. Base is given by B by 3. Here you have seen the base is B by 3. Half base into altitude. Half base, this base is this distance is b by 3 tan phi, half base into altitude. Altitude is um, again this region, altitude is this, which is b by 2. So, you get b by half base into altitude b by 2, b square tan phi by 8. Let us see how it became 8. Half base b by b by 3 tan phi into b by 2. Well, this problem needs, I think they have made a mistake here. Anyway, it's b by 3 b square tan phi by 8, b square L b square tan phi by 8, and this is the TCB is the transverse center of gravity, this distance, it is equal to b by 3, that is b by 3, and moment is the product of these two, which is L b cubed tan phi by 3 into 8, and similarly there is an emerged wedge. For that, the volume is just the negative of this, whatever is submerged is equal to whatever is emerged. So, minus L b square tan phi by 8, and this is equal to moment is the same, L b cubed tan phi by 3 into 8, and this is also same, minus 2b into b by 3, which is minus b by 3. So, for the total we will have summing this up, summing the submerged wedge and the emerged wedge and the initial, we have the total is LBT. This summing up the moments we get LB cube tan phi by 12, and moment, the total moment divided by the total volume gives you the net TCB, that is equal to LB cubed tan phi by 12 divided by LBT, which is equal to b square tan phi by 12. So, n to L, no, L is cancelled, sorry, b square tan phi by 12 into T. So, b square tan phi by 12 into T will give you the the net TCB of the whole system after it submerges and emerges. Now, similarly, we need to find the vertical center of buoyancy. This is again following the same procedure. I will just this is to find the vertical center of buoyancy. What we need to do is again solid volume VCB of that portion and the moment. So, you have first the initial, that is always equal to LBT, this is 0 0, then you have the submerged wedge, volume is LB square tan phi by 8, then this is B tan phi by 3 into 2. This is the vertical center of buoyancy of the total cone of the submerged wedge. the total the center of it is the vertical center of buoyancy of the submerged portion. Vertical center of buoyancy means this region, this height, this is the vertical center of buoyancy of the emerged region. It is equal to, as you can see, 1 by 3 of the distance from here, 1 by 3 of b by 2 tan phi. This distance whole is equal to b by 2 tan phi. So, this distance will be equal to b by 2 tan phi is 1 by 3. So, 1 by 3 of b by 2 tan phi, that is what this is, b tan phi by 3 into 2. So, the moment is a product of these two, which is equal to L b cubed tan square phi by 8 into 3 into 2. So, this 8 into 3 into 2, just the product of these two will give you the submerged wedge moment. Then we will have the emerged wedge, its volume will be negative LB square tan phi by 8, and this will be negative B tan phi by 3 into 2. Again, nothing to explain because it is just this region, this height, this height. So, that region is equal to the negative, it is then equal, it is in the opposite direction. So, it is negative of that. So, this moment is again positive L b cubed tan square phi by 8 into 3 into 2. So, for the total thing, for the total parallelepipedic barge, volume is equal to LBT and moment is the sum of these two, which is 2, this twice LB cubed tan square phi by 8 into 3 into 2, and the net VCB is given by this moment divided by this volume, which is LB cubed tan square phi by 8 into 3 into 2 into divided by LBT. So, this becomes equal to LB cubed tan square phi by, no sorry, it will become equal to B square tan square phi by 24t. A3 is a 24, there is a 2 here, there was a 2 here. So, this 2 into 2 will cancel. Therefore, this becomes B square tan square phi by 24t. So, this is equal to the VCB of the net system. VCB of the net system is equal to B square tan square phi by 24t. So, this gives you the VCB for the entire system. So, therefore, we have calculated the TCB and VCB of the entire system. Now, we have seen that as a result of the movement of the barge, the box shaped barge, because of its movement, it is tilted in one side has submerged, another side has emerged, and the side that has submerged has a new center of buoyancy, or not the center that has emerged, the center that is inside the water, the body that is inside the water, the amount of body inside the water has a center of buoyancy that is slightly displaced from its original position. As you have seen, initially it was at the center, TCB was 0, and then this system shifted to the new point B immersed. Similarly, a small region came out on the other side, which is equal to B emerged. So, the two BIs, they will be symmetrical because we are talking about box shaped barges, and all the systems we are talking about have this symmetrical inclining and symmetrical heeling, as a result of which what comes out is equal to the volume that goes in, volume that comes out is equal to the volume that goes in. So, that is that problem, and now you will get therefore, y is equal to 1 by 12. From the previous what we have done, we get like this, y of the center of buoyancy is equal to 1 by 12, the y of the entire system, the centroid of the entire system, the TCB is this, that is the y, TCB is the y, and the VCB is the z, z is equal to 1 by 24 b square tan square phi by t. Now, from this if we try to get a relationship between z and y, we get z is equal to 6t by b square into y square. This is the equation of a parabola. So, this is a relation between z and y, and it is an equation for a parabola. Now, to get the slope of the equation, we need to get dz by dy. This is equal to dz by d phi divided by dy by d phi. That is equal to dz by d phi is equal to b square tan phi. Tan phi is cot square phi. So, just differentiate this and differentiate this, you will with respect to phi. Tan phi is cot square phi. So, like that you differentiate and you will get dz by dy is equal to tan phi. It just becomes equal to tan phi. So, and if this is the equation of the b, dz by dy gives the equation of b. This is the equation of b actually. We call it as the equation of the b curve. So, b curve, similarly there are more complicated equations for the m curve, which is the metacenter's position. That is the position of the metacenter that that is given by the equation of the m curve. Right now we have the equation of the b curve. So, this can also be done using the original formulas that we had, like Bm is equal to I by del, and then Xb is equal to Ixy by del tan phi, Zb is equal to half I by for example, you can have, if you use the original equation, you will have Yb is equal to 1 by 12 b square by t tan phi. This comes from I by del tan phi. I by del, if you have I by del, I mean Yb is equal to I by del tan phi, that we have seen in some of our previous derivations. Yb, which is the transverse center of buoyancy, the transverse point of the center of buoyancy, that is given by I by del. Bm is equal to I by del, and Yb is equal to Bm tan phi. That is how we derived that expression for Bm. So, using that, Yb is equal to I by del tan phi, and what is Ib? What is I? I is the centroid, I is the moment of inertia of the system about the longitudinal axis. The moment of inertia of the system about the longitudinal axis gives you the transverse moment of inertia. So, this I transverse divided by del tan phi, this is Yb, this is equal to I transverse is equal to L b square by 12, L b cube by 12 will give you the for a rectangle. If you want to find the, if this is b, and this is L, and if you need to find out the moment of inertia about this line, then that is equal to L b cubed by 12. So, L b cubed by 12 into 1 by delta is L b t into tan phi, that is equal to L cancelled, 1 b is cancelled. So, b square by 12 t tan phi. So, this is what we got in the previous expression also. By the more complicated procedure of finding out the centroid and solving it, we can just use this expression of Yb is equal to I by del tan phi, and we can get the same expression very quickly. So, this is this concludes this chapter in this section, and now we go into something else, which what we call as numerical integration in naval architecture. We will be talking about we will be talking about the different forms in which we can do integration. There are two forms generally used in naval architecture. They are known as the trapezoidal rule and the Simpsons rule. These are two methods used in naval architecture, the trapezoidal rule and the Simpsons rule. Our idea is to find integral a to b f of x dx. So, this is our goal, to find the integral f of x dx. Now, if you divide the region from a to b into n intervals, that is I equals 1 to up to n, then you will get integral a to b f of x dx can be approximated by sigma I equals 1 to n a I into f of x I. This we will see how this is done, that is, how do you get this a I f of x I. Here a I is known as a multiplier, and in some mathematics books they are called as weights. These are different weights that are used for the different f of x i's. F of x I is the f value of f of x at different i's, different I, that is I goes from 1 to n, and f of x I goes from f of x1 to f of x n, and it is multiplied by a I, a1, a2, a3, like that, different, and these are known as the multipliers or the weights. A i's are known as the multipliers or weights. Then in some cases we have what they do is, when they do a to b f of x dx is, you replace f of x by a polynomial p of x, and therefore f of x dx will become equivalent to of p of x dx. That is the where p of x is equal to the polynomial that substitutes for f of x. So, this comes here. Now, let us do the trapezoidal rule. Okay. Now, consider this to be f of x. Okay. This equation is f of x, and these are different x's, x1, x2, x3, x4 and x5. These are the different xi values, x1, x2, x3, x4, x5, and it has the corresponding values f of x1, f of x2, f of x3, f of x4 and f of x5. So, these are the different values of f of x. Now, suppose we replace these f of x's by straight lines like this, like this, like this and like this. So, these f of x values have been replaced by straight lines, and these straight lines represent the values of f of x, that is it this f of x is now replaced by these straight lines. So, what do you get? I, if it is an integral, we can always say that I is the integral from, what we are trying to do is integral from x1 to x5 of f of x dx. This is what we are trying to do. Now, this I is equal to, therefore, we always know that I is the always the moment of always the I, the integral is a sum of is the area under the curve. We know that integral is always given by the area under the curve. So, what we want is the area under this curve. Now, as I said before, we have replaced f of x by these straight lines, and therefore, we can say that I is equal to the area under this curve. A small region here is left out, which is the error in this calculations. This whole area is left out. This is the error in our simulations, that is we try to minimize it, but it comes like this x2 minus. So, we try to find the area under the curve. It is the area of these 4 trapeziums. So, our area under the curve is the area under these 4 trapeziums. This is one trapezium, this area, under this trapezium. So, it is given by x2 minus x1 into plus x3 minus x2 into f of x2 plus f of x3 divided by 2 plus so on. This gives you the area under the curve. This is the area of the first trapezium, this is the area of the second trapezium. Like that, you have areas of 4 trapeziums. This I is equal to, let us suppose that first of all let us assume that x2 minus x1 is equal to x3 minus x2 is equal to all of them is equal to h. Therefore, we get this whole expression I is equal to half, coming from here, half h into, or h into half f of x1. There is an f of x1 here and f of x2, and there is an f of x2 here. So, half f of x2 plus half of x2 gives you a one full f of x2 plus f of x2 plus f of x3 plus f of x4 plus half f of x5. So, this gives you the area under the curve, and similarly for if you have n such numbers, then I is equal to h into half f of x1 plus f of x2 plus so on till f of x n minus 1 plus half f of x n. So, you will get an expression like this. This is the expression for the trapezoidal rule. This is the expression for the trapezoidal rule which is followed in naval architecture. Now, for instance, you might be having a problem like find integral 0 to 90 sin x dx. Suppose we have a problem like this, then this is how we solve the problem according to the trapezoidal rule. The analytical form of the solution would be equal to 1. As you can see, it is cos x. So, it will become minus cos x. So, it will become cos 90, that is 0 minus cos x. So, 0 minus 1 which is equal to plus 1. 1 is the answer to this problem. It is 0 to 1 x dx. So, if we have to do it using the trapezoidal rule, we do it like this. Angle, this is sin x, multiplier, product. So, these are, so first of all we will divide this in terms of 15 degrees. So, 0, 15, 30, 45, 60, 75 and 90. So, this will be the region in which we divide. So, sin x 0, multiplier is half, product is 0, 0.2, sine 15 is 0.2588, this is 1 and the product is 0.2588, sine 30 is 0.50, this is 1, so this is 0.50, sine 45 is equal to 0.707, this is 1, 0.707, sine 60 is 0.866, 1.866, sine this is 0.9659, 1.9659, sine 90 is equal to 1 and this is half, so it is equal to 0.50. So, this gives you the whole list of terms, and so what do you have? Your expression is, first of all, how much is this h? We have to figure out h first. It is uniform, h is equal to pi into 15 by 180. You can see here we are doing it in terms of 15 degrees. So, pi is 180 degrees. So, this 15 degrees interval is equal to pi into 15 by 180. So, once you have that h, you have the sum of the total. The total comes to 3.7979. So, h into this total 3.7979, that comes to 0.9943. This is the expression for the sine, this is the expression for the integral of sine 90, sine integral of sine x between 0 and 90 degrees. This is the expression, this is the answer, and comparing to 1 we see that we have got a fairly very good answer. This is how you do it. And similarly, when you do it, you get you will always be having an error in doing the calculation. There is always an error in it, but I will skip over the region of error because that is not used mostly in this in our studies. In this course we are not going to use that. So, but there is definitely, understand that, remember that there is always some error associated with this, and then the next is another method that is known as the Simpsons rule. This is known as Simpsons rule. What we do is we replace f of x by a0 plus a1x plus a2x square, that is a parabola. So, the situation will look like this. So, this is equal to your f of x, and this you are replacing with a parabola, proper parabola, and this parabola will be, and therefore we have here a parallelogram it actually comes like this. Okay, actually this figure hasn't come out properly, let me draw it further. So, this is your f of x. We draw a parallelogram like this. This distance is equal to this distance, and it's a parallelogram, and the whole thing is replaced by a parabola. So, this is the system is as if a we have a parabola inscribed in a parallelogram, in that is what this thing is about. So, here you have this B H C G I D so you have AB. Actually this is a slightly long derivation, and since we have fallen out of time, we have only 5 minutes left. So, I will leave this derivation for the next class. We will do this integration in the next class. So, I will stop here now. Thank you.